Okay, let's get started. It is my great honor to have this wonderful lecture by Professor George Smoot today, the Nobel laureate of physics. And without further, there will be some more introduction. Now I would like to introduce our president, Eun-hee Kim, for welcome remark. Please give a big hand.
Good afternoon, everyone. Distinguished Professor George Smoot, professors and students of Ewha, distinguished guests, ladies and gentlemen, welcome to Ewha Women's University. My name is Eun-hee Kim, and I'm the president of Ewha Women's University. I would like to thank the Korean Academy of Science and Technology and the Nobel Prize Outreach for hosting this very important academic event at Ewha. It is particularly meaningful that you have selected Ewha to bring Professor Smoot to deliver a special lecture. Not only did Professor Smoot spend 5 years since 2009 to create and build the Institute for Early Universe at Ewha to educate and conduct research with our students and faculty, but Ewha is an all-women's education institution of higher education, striving to educate and train women scientists and engineers, as well as in all other academic disciplines. According to the Global Gender Gap Report 2023, the world is 131 years away from reaching gender equality. In education, we're doing better, but higher education is another story. In particular, when it comes to STEM, that is science, technology, engineering, and mathematics, there are only 18% of girls pursue STEM fields in tertiary education, that is higher education, vis-a-vis 35% of boys around the world, according to the UNICEF study that was conducted in 2020, mapping gender equality in STEM from school to work. And only 28% of the STEM workforce are occupied by women, according to the 2022-23 research published by MIT. There are other studies that show that during COVID-19, more girls than boys dropped out of school, and women scientists published, and this is statistically significant, less in scientific journals across the world, which all point to challenges women and girls face in education and work, especially in STEM fields. Thus, it is particularly poignant that Professor Smoot is here at Ewha, which was founded 137 years ago as an all-women's education institution in Joseon, Korea, when Confucian tradition did not allow women to be educated. So Ewha was established with the sole purpose to educate and train women to become the best in all academic disciplines, including science, engineering, and medicine, by women missionaries from the Women's Foreign Missionary Society of the Methodist Church of the United States. Mary F. Scranton, who founded Ewha, came to Joseon to educate women and girls who had no opportunity for education before Ewha. We have kept that tradition of providing the best education for women. Ewha is now a top research university with 15 undergraduate colleges, 15 graduate schools, and 2 teaching hospitals with 1,000 beds each, with 25,000 students and 250,000 alumni around the world. There is no such women's higher education institution in the world. Thus, it is my utmost honor and privilege to introduce Professor George Smoot of the Hong Kong University of Science and Technology to you today as our distinguished speaker at Ewha Women's University. Professor Smoot, as you all know, is a Nobel laureate of physics in 2006. He received the Nobel Prize jointly with Professor John Mather for their groundbreaking work on the early universe and the Big Bang theory. We are delighted to welcome him back to Ewha. Professor Smoot played a crucial role in founding the Institute for the Early Universe at Iwa in 2009 and served as its director for 5 years. During that time, he was deeply involved in research and education of cosmology and space at Iwa, and Iwa's faculty and students have been proud to have maintained that partnership with him over the years. I hope his lecture on cosmology today will inspire Iwa students and many others who have joined us today so that they will be inspired to become the next generation's great scientists in physics and other fields of science. I hope you will inspire our Iwa faculty and students so that Iwa can be the first institution to celebrate the first Nobel Prize in Sciences in the Republic of Korea. Yay! Please help me welcome Professor Smoot to the podium with a warm round of applause. Professor Smoot. Oh, no, we do have another introduction. Sorry about that. Mr. Adam Smith.
Maybe this one is. I don't know. This one is working, yes. I'm sorry to disappoint you all by not being George Smoot. You just have to wait. Yeah, he used to have the beard. I've got George's beard. That's about as much of George as I've got, I'm afraid. Anyway, just 2 minutes before you get the real man. I'm Adam Smith. I'm the Chief Scientific Officer at Nobel Prize Outreach, which is the outreach organization connected to the Nobel Foundation in Stockholm, Sweden. And on behalf of all my colleagues in Stockholm, I would like to welcome you to this lecture. One of the most important things we do in Nobel Prize Outreach is to take Nobel laureates around the world to meet the next generation of scientists. We do it on 5 continents. We've been doing it for many years, and it is a great delight to be here at Iwa, bringing George back to this home of his to meet you all. And I'd like to thank Iwa for so warmly hosting us, and President Kim especially for her kindness. Thank you very, very much indeed. The reason we're in Seoul at the moment is that yesterday we held something called the Nobel Prize Dialogue, which is a big meeting we hold in various countries around the world about 3 or 4 times a year. This one was organized in collaboration with the Korean Academy of Science and Technology, with whom we have a long-standing relationship. And the meeting was on the future of education, held at COEX, and we brought together Nobel laureates and experts from around the world and from Korea to talk about it. And particular discussions focused on exactly what President Kim was talking about, the role and challenge of diversity in STEM. And there was particular concentration given to the fact that although there is nice gender diversity and interest in STEM subjects at school, it wanes as you go on, and the particular problem of career progression for women in STEM subjects. So if you would like to take a look at those discussions that happened yesterday, they are available to see on nobelprize.org. And I would like, please, to thank the partners who are named up there, who allow us to organize such meetings, their generous support, and be here today. Now, I'm going to hand over to George Smoot, who is the 2006 Nobel laureate in physics, as you well know. George is untiringly inquisitive, and every time I've seen him give a lecture, it has been the latest lecture. He updates it right up to the last minute with the latest news, and that's quite unusual. It also means that he tends not to have given this lecture before, because this one was created entirely new for you. That means he doesn't know how long it is. So if you see me waving furiously at him at some point, that means, George, you've got to think about stopping at some point so that we've got time for Q&A, because Q&A is an important part of this. And I would very much like to leave time for George and myself to sit up here and get your questions at the end of the lecture. That's it from me. George, now the floor is yours. Thank you.
It's a pleasure for me to be back here at Iwa. I don't know almost any of you because it's been 9 years since I was here on a regular basis. So a couple of whole classes have graduated, but I had a lot of experience and I taught a lot. I actually even gave a lecture either in the hall next door or this hall some years ago, but mostly I taught down in the new slot building because that's where the classes in English were done. And I don't know about now, But in those days, Iwa was proudly advertising that at least a quarter of your classes would be in English. So you're all supposed to know how to speak English. It's, I assume the same thing is going on today. And I got to figure out how this is going to work. And as Adam said, I had, this is going to be a surprise lecture for all of us because the last week I was in China and my 2 VPNs that I use in China didn't work, so I couldn't do that. And before that, I was busy getting ready to those talks for in China, but Douglas Scott and I, and you'll see one of our products, every 2 years write a review of the status of the cosmic background radiation, which is the relic radiation from the Big Bang. We write a review about that, and we've been doing that for 20 years, so we're on the 10th iteration. And I was just impressed by how progress has been made. I look back at the early reviews and I look at now, and I'm going, oh, wow. And then I thought, well, you know what I should do for the talk? I should show how we really understand things and things interlock together so well. If you just try and change one thing, it screws up all the observations. That it's a real difference between science and certain conspiracy theories in that you can't just make it up. There's so many things that are interlocking together and mathematically work out that you cannot just change that. And we give talks and we say, well, we don't know what dark matter is. Actually, we know a lot about them. We just don't have samples because they're really hard to get. So with all that preamble, I will try and start the lecture and try and convince you, since I started in this field and made some key discoveries, we have made unbelievably incredible progress in understanding the universe. And we can say there was something that happened at the beginning, and we began to create space-time in the universe. And the first thing that happened was the creation of all the space and the time. And the next thing that happened is, because of quantum mechanical fluctuations during that process, we then got the interesting structure. We got the things that turned out to be galaxies and clusters of galaxies, and eventually turned into stars. And then they took the universe and ionized it so the light could get through very cleanly, and we can look back and we can see early galaxies and early stars. And one of the things that I have a graduate student and a postdoc, and we're part of a bigger team working with the James Webb Space Telescope. We're looking at the very first galaxies. We're using clusters of galaxies as lenses to augment the telescope so that we can see what the very first galaxies look like. I don't know, there's been surprises, but they don't happen before the beginning of the universe. They happen in that region which we call the dark days. But, you know, something's going on there we don't quite understand, but it doesn't screw up the big picture. I'm still confident that we know what we're doing. It's just, you know, there's always hope, and it's exciting because new stuff is coming in all the time, and that's what I'm trying to give you a flavor for. Okay, so let's go back a little ways just to show, because when I first started giving lectures about cosmology, there were only 4 things we knew. I could give an hour lecture, I could tell you everything in cosmology, and I could give you the logical reasons, and that was it. And the first thing was Hubble made the first universal law that the universe is expanding at a rate that's uniform. That is, the velocity at which you're receding, apparently receding, is just proportional to the distance you are away. And so Edwin Hubble got to be on the biggest telescope of its day. There's a picture of it down there. It's pretty crude looking, but, you know, it's actually really cool when you see those old, you know, kind of telescopes. This one's at least a reflector. The earlier ones were refractors, that is, lenses you look through. And he discovered the stars and nebulae were pulsing, and their brightness and their pulsation rate were tightly related. In fact, there's a woman who discovered that. She gets some credit, but he gets the credit for using that as a tool to making the discovery that the universe is expanding. Right? And so he measured Andromeda Galaxy. This was a big breakthrough. He proved that Andromeda Galaxy was not in our galaxy, that it was far enough away. And that means there was at least 2 galaxies in the universe. Before that, many people thought there was only one galaxy and then empty space. Right? But as soon as you prove this is a galaxy as big as our own galaxy, that's outside of our galaxy, is a whole new ballgame. Now we know there are hundreds of billions of galaxies out there. So it's a different ballgame. So there's the moon, pretty close by. There's Andromeda. You know, it's 2 million light years away. It's time's different, right? And then the sizes get big. Whoops, my button pusher. Oh, I went too hard. Okay, so how did he measure it? He measured the thing that we call the redshift. What he noticed was that except for 2 galaxies, every external galaxy you look at, the light from that galaxy is shifted to the red, and the further away the galaxy is, the more it's shifted to the red. And in fact, it's a pretty much linear relationship. This is some of his data. I'll show you his real data, but this is, you know, here's the distance and here's the apparent recession velocity. This is interpreted as a Doppler shift. That is, if you hear a train going away, you'll notice that the train whistle is lower pitch. That's the Doppler effect. And this is the train going away. All the galaxies but 2 are going away from us. Okay, they don't like us, or the universe is expanding. Your pick. Okay, so here's the plot. And what you do is you see there are certain lines, and you look at these lines and you see how much they're shifted. And it's easy to do. You put a prism up or a grating up, put the light through, it spreads the stuff out according to wavelength. You just measure the wavelength. It's done. You got this nice plot. You have to estimate the distance. He got the distances wrong, but at least he was within an order of magnitude of correct. Well, within 2 orders of magnitude of correct. And he got the velocity very right. But you can see that that's not much data to make the claim that the universe is expanding uniformly everywhere. You have to make certain jumps to what's going on. Okay, so let's talk a little bit about how this measurement was made. God, I can trust my button pushing better. Okay, so here is a little glowing tube with electrical discharge that has hydrogen in it, and you see a line, that's in the red, and then in the blue and in the ultraviolet and so forth. These is known as the H alpha. There's 3 series of lines from hydrogen atoms. And so the H alpha is the brightest one, H beta, and so on. You see these lines, you know there's hydrogen. Well, hydrogen is the most common element in the universe, makes up about 85%. Helium makes up another 20%, right, which is already 105%, and everything else makes up, 1%. So you got this. Let's see, I keep pushing the button because I trust it. And you can actually look at what was going on because studying these spectra gave us the interlocking information during that time period. First, people found the spectra, and then they started to try and understand it. They discovered helium. You know how helium was discovered? Looking at lines from the sun, and there were lines there, and when they started writing these formulas for how the lines come from an element, it's clear that something with a charge of 2, a mass of 4, existed in the sun, and they looked around, and they eventually found it on the Earth, because you can find helium on the Earth too. That's good for superconductivity. So there are sets of lines, depending on whether you're talking about the highest, an electron jumping from one level to the next, and which set of levels, whether you go to the most innermost level, or you go to the next level, and so forth. So there's the Lyman series, the Balmer series, the Passion, one was Greek letters, the other way is named after the people who discovered the series and figured out that they were going on. And that's turns out to be true for all the elements. They have discrete lines, and if you get them in a very nice condition, those lines are extraordinarily sharp. If you have them in a place where they're all pressed together, the pressure and the banging around spreads them out. But you still see the lines, and you can measure them very carefully. Now, that tells you that things are quantized, because it's not just uniform set of, they're actual quanta. And then when you look, my physics colleagues are shaking their head, you can look, there's a fine structure. That is, if they're in a magnetic field, like you're looking at the sun, there's magnetic fields, you will see that line has got a tiny split, usually a doublet, and it's just proportional That split is proportional to the electric field and the magnetic moment of an electron. So electrons have spin a half, but they always have spin up or spin down. It's completely quantized. There's no other choices, even though in real life, when you have a top spinning around, you can move it around and point it any way you want. In nature, things are quantized. And you keep going and doing this kind of stuff, and you see this spine splitting, and then there's a thing called a hyperspine splitting that has to do with how the nuclear spins are and so forth. And there's a series of things like that, and you could do that, and all these things fit together very tightly in a weave. It's extremely difficult to challenge quantum mechanics as being a real thing, right? Now it's going to be important because we're going to use quantum mechanics to make the universe. So it's, it was God's plan to make the universe by using quantum mechanics. Okay, so here we are. Here's a nebula. You look out at it. You see the hydrogen is present. Sometimes you see other elements along the way, but you see this is a real sample, and this actually has two sets of hydrogen, one moving more towards us than the other one. So I got to use this button. Get it through in a reasonable time. Here's a galaxy that's a little further away. Now you can see the broad background, but you can see the Lyman, age alpha, and you see it shifted a little more to the red. And you go a little further out, and you see, again, another galaxy. It's a smaller galaxy. It's smaller because it's further away. It's actually the same size galaxy in this case. Sometimes they are smaller, sometimes they're larger. The line's moved again. It's moved further to the red. And so on. You keep doing. This is even a harder galaxy to see. You need a bigger telescope. But you can see it's moving away from us. And go further, and it's going further. It's now out of the red into the infrared, or the near infrared, and so on. And this is a galaxy that's really tiny looking because it's actually pretty far away. And there again, you can see the line is almost off the edge of the spectrograph here. You have to use a different kind of spectrograph to see it. And here's the actual real Hubble data. See if my light button works. Well, here's the actual original Hubble data, where he did it for individual galaxies and groups of galaxies, and his estimate of how far away it was and what the effective expansion rate was. And here is kind of a present day set of data. So Hubble's original data fits down in here. And it's kind of sloppy, to make a universal law. Now it goes way up. Now I have to use a somewhat more complicated quantity, because a star or whatever it is that has kind of a black body curve, if you move it into the redshift, you're moving where the intensity is different. You have to correct for that, call it K correction, because all the wavelengths have changed, and you're measuring with a fixed filter. You have to make an adjustment for that. You make adjustments for other things. But basically, is your straight line. It's pretty good. This with low Z supernova and measurements. This is Sloan Digital Sky Survey, the extension of the Sloan Digital Sky Survey, and the Hubble Space Telescope. I mean, that's the straight line. Here's the residuals. If you fit that line and subtract it and look at the residuals looking for waves or structure, it's pretty straight. That means, from our point of view, the universe is expanding uniformly in all the directions that we've looked at galaxies and measured things carefully. Well, that's actual progress. And in fact, we're looking further than that now I'll show you that with JWST and gravitational lenses, we're looking out to a redshift not of 1. This is roughly 1, so 1 almost to 2, slightly off this. We're looking out now to a redshift of 8 typically. We were able to find stuff that distance. So the universe is expanding, and we have to now take into effect that when light starts out from these things, it starts out from a smaller universe, and it starts out from a universe that wasn't expanding at always at the same speed. The speed at which the universe is expanding has changed some with time. So we get to measure all those properties. Okay, so now we have this sort of vision. I made this picture long ago, and I like it so much, so I keep it. There's the beginning of time. There's the thing we call inflation, where we're creating space-time in a really major way. That is like 10 to the minus 30th seconds. We make up a universe that's halfway between the beginning of time and now in terms of how much it's grown. So half the job was done in the time it takes light to travel this distance. Well, I'm exaggerating so you can see there's a gap, right? It is amazing, right? How can you make this up? How do you know this? Well, because when you make things that small, quantum mechanics becomes important, and you get little fluctuations. And those little fluctuations, as tiny as they are, that's what I got the Nobel Prize for discovering. You know, there are parts in 100,000. A billiard ball is 10 times more coarse than that, if you know what that is. So the universe was almost perfect, but the imperfections in the universe is what make it really interesting, what make it so we have stars and galaxies and planets and life. It's kind of neat. And all we got to do is wait 13.7 billion years, and here we are. We got galaxies, we got the Earth, we got the audience. No problem. Yeah, it was an easy thing to do. The starting was the hard part. Okay, so I used to do this talk. I went in one of my early talks was the 25th anniversary of the discovery of the cosmic microwave background. When I fixed up this slide, I had to put 59. That means we got to plan some kind of a certain celebration next year, but we'll see. And I spent, before I was working on COBE and the stuff that did that, I spent a bunch of time trying to measure the spectrum of the cosmic background. If this idea of the Big Bang is correct, it will simply be thermal radiation because the early universe was hot and dense, and it was in extraordinarily good thermal equilibrium. What do you get when you do that? Well, you get the black body radiation. Well, that's black body radiation. With COBE 5S, the instrument that John Mather was head of, we measure the peak, which is 90% of the energy, but we measured the long tail all the way down to Penzias and Wilson's discovery, right? So you see on this plot the reason why 4 people got the Nobel Prize. One discovering it, one measuring the spectrum, and one measuring these fluctuations. And so I made these plots back in 1992. The universe is extraordinarily uniform. That's that plot there, just below that. There is a anisotropy where it's hot in one direction, cold in the other, and there's some spots that turn out to be right along the galactic plane. If you ignore the galactic plane, that's simply the Earth moving relative to the distant matter in the universe through the radiations for the rest, through the zero momentum frame for the radiation field. But when you remove that, then you see the galaxy much stronger because you have to go down another factor of 100 before you start seeing the variations. And that's the beginning of the trip of where people started saying, hey, let's take this seriously now. This looks good, right? And it really is the kind of situation where at the time I was convinced that it was science and physics could be done. And somehow I had the confidence if we keep making measurements and everything, it would all fit together. Now it fits together too much. Now people are trying to tease it apart to find out these little anomalies and do that. But the problem is there's not enough anomalies to go around, and the scientists all want to make great discoveries. Well, sometimes you're at a plateau and you're really making progress. So the other thing that came along during this sort of time period is the Hubble Space Telescope. The Hubble Space Telescope looks out at the universe, and they go on about how big it is. It doesn't look very far. You know, here with COBE and the ground-based and balloon-borne experiments and stuff we're looking back practically to the Big Bang. You know, Hubble is looking at galaxies out when the universe is roughly half the size it is now. On the Hubble Extra Deep Field, right, they're looking out, you know, where it's essentially 2.7 times smaller than it is now because the universe has been expanding. You can go back a long way. That's the Hubble Deep Field, and there the Hubble was running out of gas in terms of being able to do it. Now, with the JWST, which is designed to look in the infrared because light is from further away, it's been transported more, we're starting to look out through here, but we have to use these gravitational lensing to give us the boost in power in order to see the things from before that. But okay, let's continue on this one. When when you start fitting the data together, theorists want a flat universe. Well, why? Well, it kind of looks flat, but it's easier to do the calculations. There's a bunch of other stuff. So here's the thing where it's how much matter there is and how much dark energy, which we didn't know about. But again, that's another Nobel Prize for Miller and Adam Rees and so forth. There are three of them got the Nobel Prize for discovering that the universe is expanding more and more rapidly these days. And they did it by using supernova and measuring the brightness of supernova versus distance, and see it didn't follow the perfect curve that you would expect if the universe was just slowing down from gravity. That in fact something is causing the universe. And that's when we started saying, all right, we got to take the dark energy seriously because it actually can make the universe expand faster. And then you can use either what's called Baryon acoustic oscillations. The fact that if you have these perturbations in the early universe and the speed of sound is driven by light, so things oscillate faster than they can collapse. So you get baryon acoustic oscillations, you get acoustic oscillations, or you could just simply count up clusters of galaxies, and both of them fitting on these data tell you you want to be somewhere near a flat universe with about 2/3 dark energy, about 30%, right, made of matter, but of that matter, most of it's dark matter. So, we got this name lambda CDM model because it turns out Einstein's cosmological constant acts like the dark energy too. And lambda is easier to write than dark energy. All right. I haven't learned to push the button right. So if you now look at the energy budget of the universe the way we thought it, this particular one, it varies around a little bit in the early days. It's 70% dark energy, 25% dark matter, 4% hydrogen helium, which is most of the matter in the ordinary kind of matter in the universe, because it mostly hasn't, it's in stars or in gas cloud, but it hasn't burned in the higher elements like carbon, nitrogen, oxygen, and iron and so forth. So stars are only 0.5% of all the energy budget of the universe. And neutrinos, which are all flying around everywhere, through my hand, there's this number of neutrinos, a significant number of neutrinos per second, and they're flying around all over the place, everywhere in the universe. They still have only 1/3% of the energy in the universe. And the heavy elements, the stuff that we see the floor made out of and things like that, that's hardly noticeable, right? Sort of a little humbling. Okay, so we're not going to really use this math, but I want you to know you can use math. And it's science when you do math and you calculate and you get numbers and you compare them to the outside world, and that's what agrees, right? And so this Alexander Friedman took Einstein's equations of general relativity, said, let's imagine we have a universe that's isotropic and homogeneous. That is, I can instead of having this 4x4 matrix of differential equations to solve, I can simplify it to two differential equations for just simply the scale factor of the universe. The universe is either getting bigger or getting smaller, right? It's got a choice in terms of what's going on if you're going to make it so that it's the same everywhere and uniform in all directions. And so you find there's a kinetic energy kind of one that says the expansion rate of the scale factor of the universe plus the energy density in the universe minus the curvature of the universe are equal. That's just conservation of kinetic energy or total energy. And the other one is the force equation, the second derivative. The acceleration of the scale factor of the universe just depends on the energy density and the pressure density, right? And so forth. And you have to include the pressure because something you can say, what if I have a gas ball, I have a lot of pressure in it, doesn't that stop it from collapsing? Well, it does locally, but it doesn't stop the universe if you make it big enough. In fact, because they contribute positively. So you're going to collapse, you're going to slow down, you're going to collapse. So dark energy is amazing because it's got the different signs. You need a negative pressure to make it work. I think I had another plot, just another one of the same equation. This is, you can get this equation without general relativity or anything else. All you have to do is assume the universe is the same everywhere and the same in every direction. And you go and solve for what are possible. It's basically a spherical universe, but a spherical or hyperbolic universe You don't actually need general relativity. You don't actually need anything else in order to get to that. Okay, so once you've got that, and once you've got the idea that you have quantum fluctuations in the early universe, then you've got interesting things going on. And then it goes crazy. Okay, so there's the COBE map that my team and I were responsible for. Then it was followed by the Wilkinson microwave anisotropy probe. And then more recently, the Planck mission. One of the reasons that I live in Paris these days, part of the time, was because of the Planck mission. And a prediction that I and other people made that there should be a spectrum of temperatures because there should be fluctuations of equal level. If the quantum fluctuations are going on, they go outside the horizon and the expansion, and they're all happening at roughly the same rate. It'll tilt slightly depending on speeding up or slowing down, but it's basically the same. But then you have these perturbations, and the light tries to blow it apart, and the gravity tries to pull it together, and you get these oscillations, and those oscillations are those peaks that you see. But once you realize that, you have a fluid sloshing around, it's like ringing a bell. You can tell a lot about the properties of the bell by listening to how it, the tone and the ring and the frequencies that are involved. The same thing is true. We ding the early universe, we get to hear it ring, we listen to the sound, we can tell how close it is to flat, we can tell what quantities it's made out of and so forth. So with COBE, we were measuring what's called a Sachs-Wolf, that is stuff that's inside the horizon and hasn't had time to change, even though the universe was at that time, you know, some number of million years old when we got a snapshot of it. But when you go further out, you start seeing the acoustic oscillations. The WMAP started probing those that were in the first three. Before WMAP went, I and my colleagues were doing a balloon-borne experiment. We started seeing the first peak and part of the second peak, and 2 or 3 other groups did that. So that by the time WMAP actually came out, we already knew it was there. What WMAP did was make the precision much better. And then we did Planck, and Planck got out. You'll see we actually have 7 peaks we see in this kind of thing. Right? I don't have them all here, but that's the kind of progress we're doing, right? From the time we did this stuff 30 years ago till the stuff we put out, 5 years ago, we went from seeing no peaks to 1 peak to 2 peaks to 3 peaks to 7 peaks, right? I mean, when you got that many peaks, it's not quite as clean as those hydrogen lines, but they better all fit together. They ought to fit just like the hydrogen lines kind of things do. Okay, so to show you how this kind of looks, look at this curve. It shows you the data from Planck, from the Atacama telescope, the South Pole telescope, the other Atacama polarization telescope in the South Pole. Look at those peaks. This is the spectrum now. We're starting to see spectra, right? We're starting to see spectra of the ringing of the universe. But we haven't started to. We're seeing a lot of it. And depends on how much you want to believe, you might see some wiggles further out. And you start also seeing the polarization, but I'll try to come to, if I don't overrun too much, I'll try and get to the polarization. And so you can fit this to a simple model of the universe. There is inflation. There's space-time is created with these quantum fluctuations. The universe is made of dark matter, dark energy, ordinary matter, a few neutrinos. Percolate through your computer program. And you see this prediction of what the thing's going to look like. You can compare many models together, make up nice curves of likelihood of which one is the fit, and find the 6 parameters of the universe with precision that's about 1% now. That's starting to be science, right? That's starting to be a serious test of what's going on in the world. Okay? And at the same time, my colleagues and I, although I do much less on this than they do now because it's ongoing, started an idea to measure the baryon acoustic oscillations in the galaxies themselves. These baryon acoustic oscillations are big. The baryons are blown out. They fall back in the dark matter. That's so they can make the structure. You need the dark matter there to make the perturbations so the structure fall back in. But a few of the baryons are left out in the outer bubble. And that means a few extra galaxies that make bubbles all over the place. You make a map of galaxies in the universe and measure them carefully, you can see the residuals of the bubble. So in blue there, you see the extra residuals, the same things that are the peaks in the cosmic microwave background, showing up in the location of galaxies. So this is power spectrum of the angles of galaxies, but basically there are little residual spherical clusters of galaxies all throughout the universe, and they're particularly around big clusters of galaxies. So it's quite amazing, but it's exactly what you predict by running a simple physical model. And so we'll see. Now what's going on, there were several different groups that did that. The group that I was with in Berkeley, and I'm actually a member, I got an email yesterday that we just reached the halfway point for the team email saying, we're making all these observations for the deep survey. Congratulations, we're at the halfway point. The idea there, and I'll show it to you, is to measure with this robotic telescope. By robotic telescope, I mean thousands of optical fibers that get plugged in by robots into a plug plate in the telescope automatically, and you move them around. You line each one of these fibers up so that the image of the galaxy is on it, and then the fiber takes the stuff down, and the groups of fibers are put together in a long stream, 100 to 500 each, and each one of them gets their spectrum measured, right? So you're doing 1,000 spectra at a time. I forgot when I started. Am I half hour or I'm... Oh, I'm in big trouble. Okay. You guys are even worse trouble. Okay. All right. So here's a plot of what it kind of looked like before the new plot that's going to come out that's really going to be amazing. Okay. So here we are down here at the bottom. This is the Earth. And we're looking out. And you're measuring the speed, the spectra for each of the brightness and the spectra for all these galaxies. And the goal is 10 million, 50 million, something like that. You got to stay on this curve, you know, the curve of improving the number of galaxies you see on the sky, right? This is time. This is the number of millions you have. You want to have 30 million galaxies that you've measured their position and their angular position, their distance, and their redshift very precisely, so that you can measure and you can look for these acoustic oscillations. You can look for other phenomena, so you can truly understand what's happening in the time scope. So the Stolen Digital Sky Survey did basically, you know, I can't see it, so I can read it here. Basically 2 gigaparsecs cubed, right? Gigaparsecs, 1 billion parsecs, which is 3 billion light years, right? So it's big, but now we're talking 50 billion megaparsecs. Now we're starting to talk about deep. I had a question about deep space yesterday. I say, what do you mean by deep space? The moon or Pluto or, you know, the end of the survey, right? And what is on this thing? Well, as you go out to the various distances, you see all these galaxies being measured, and you see the thing that they call, you know, large red galaxies, the extra luminous galaxies and so forth. And out here you see this funny thing in green. You know what this is? Out here is a quasar, and the quasar is a quasi-stellar object, but extraordinarily bright. You can see it out to a high redshift. It really, we think, is the active galactic nucleus that has a big black hole that's doing a lot of stuff. And it shines very brightly like a star. You can then look at neutral gas clouds between you and it, because they absorb in the hydrogen and helium, but mostly in the hydrogen. You can see the absorption lines, and therefore all these little spots in here are gas clouds where you've measured the absorption line. And we're going to have like 2 million of those covering up the sky, and it's all highly correlated. So we're really beginning to study the universe carefully, and it's kind of exciting. So 1992, long time ago, 30 years ago, we had COBE. WMAP came roughly 10 years later, 20 years ago. Planck, right, 5 years ago when we were getting these results and making improvement. But there's a whole new set of experiments going on. The Simon's Array, Polar Bear, Cosmology Telescope, Ali CP2 in Tibet, Bicep Kep, going to make very high resolution measurements. And those results are starting to come in now. We're getting results, and I hopefully will be able to show you some. This is nice in this mode. The stupid viruses don't show up on that screen. They only show up on my screen. Okay. So here are some of the experiments that are done. This is the Planck experiment. That's one of the South Pole experiments. This is one of the balloon-borne experiments. That's the Planck satellite. Here's CMB City at the South Pole. Think about that. All this stuff is for doing measuring the cosmic microwave background, and it's literally at the South Pole. This trail here gets you across the runway, but there is a flag over here which marks the official South Pole. I mean, it's amazing. When I was there, it was like, oh, it's cold. We're digging holes in the ice, doing stuff. This is up in the Andes, right? And there's a city there too for measuring the cosmic microwave background. People are really highly motivated to do this stuff because we're learning a lot. And part of the thing is we've gone to the next level. Not only do we see the temperature variations, but if you have a temperature variation, if you could imagine you have something where it's it's unevenly illuminated. Imagine you're sitting in your car and the sun is shining on the hood. It reflects off. It's partly polarized. We have anisotropy in the universe. There are other things that are going on. That means the universe is slightly polarized. It's polarized at about the 5% level of the anisotropy. So this is our fine splitting, but it's not as fine as splitting it is for atomic spectra. And here's the thing. There are two kinds of modes you can imagine as patterns across the sky. Uh-oh. All right, well, the talk might be over. It might be exam time. And so you get the same phenomenon in the early universe that because you have anisotropies and because you have velocities of the acoustic velocities, you will get this polarization at the few percent level. And that polarization, you could just measure the polarization and try and put it together. But if you think about it, you will realize in terms of the physics of cosmology, there'd be two kinds. One we call the E mode because it's like an electric field. It comes from a simple scalar potential. And one that's like the B mode, which because it comes like from a magnetic potential. And in fact, it's a little more complicated. It comes from tensor kind of modes, could come from vector kind of modes. And so those are the patterns you see. The E modes are very simple. They're it's either hot and it's lined up one way, or it's cold and it's lined up the other way. And so you get either a circular pattern or a star pattern, and that's pretty clean and pretty new. And that, in fact, we know must exist because we see the anisotropies, and we believe it's due to the kind of matter that's out in the universe that's going to make the galaxies and so forth, and the dark matter. But you can also have what we call B modes. All right, well, I should have put it on there's something we don't like. All right, well, we'll quit on this. We'll quit on that page. Maybe it's something funny about that page. And so you get these two potential patterns, and the things that cause the temperature perturbations and so forth, they're scalar modes. They just come from energy density. It's a scalar. But you could imagine they're tensor modes because space-time has 4 components. If general relativity has 4 by 4 components. There'll be a tensor part, a vector part, and a scalar part. The scalar part is the time part. Everything else, right, there are vectors this way and tensors in the part. A tensor mode, when it comes inside the horizon, is a gravity wave. That, what I hope, is what's screwing everything up. And I had a moving gravity to show you. In order to get this complicated twisting pattern, you need something that has a direction, has a polarization, and has a polarization that's complicated. Whereas for the other things, all you need is more material or less material, and you get this nice kind of pattern. So starting not so long after I announced the discovery, I started the thing where we want to say there should be these tensor modes, and we want to look for them because that can tell you what's going on. The scalar modes come from the thing that drives inflation. The tensor modes are the actual motion of space-time, the creation of space-time itself, the quantum mechanics of how the tiny horizon was. So you get quantum fluctuations in the dark and the energy driving inflations. That makes the scalar modes, but you get scalar, vector, and tensor modes from the space-time fluctuations itself. So if you could measure that, that's a direct measure of the energy of inflation, but it's also a direct measure of the nature of the vacuum and everything at the beginning of the universe. So that just seemed like a really interesting kind of thing to be seeking in my day. And people have been worried about doing this for a long time. And in fact, there was even a report that people saw it. But the idea is you're going to look there and then you're going to map here. There's a thing that happens intervening. There's all that scalar matter out there, all the scalar potential. They cause, exaggerated here, gravitational deflection and gravitational lensing. That causes some of the B mode stuff to be twisted. So the the E modes, some of it get twisted to B modes, and it becomes a background for your seeking to see the nature of inflation. All right, let's see if I can get to the next message. Okay, it was something wrong with that one slide apparently. I hope. Cross my finger. Okay, so now this is what Douglas and I wrote in 2016 and 15 for our review. Over on the left side are the prediction from scalar perturbations, fitting to the normalization from Kobe out here in this region, and predicting what we see. And then there should be a correlation between the T and the E modes of polarization. There should be a signal from the E modes of polarization, and there should be some B modes that aren't really B modes. They're E modes that gravitational lensing twisted. The gravitational lensing doesn't change the energy in some way, but it can make the apparent location from where something came. So you could take, that was what that picture that kept crashing showed. Here's a pure E mode, and then you see the E mode plus a little bit of E mode because a little bit of thing went on. And here's the data. Oh my God. Look how many bumps there are. There's the temperature, here's the E modes, here's the lens B modes, right? Here's the prediction. And all of those curves come from fitting that little part down there and then predicting what the rest should be. Fits pretty well. Hard to change things without, thinking you're going to screw stuff up. All right, how come this didn't? Oh, this is to show you what we hope to do for the next satellite. We hope to fill in this region down here where the possible signal might be for seeing the actual fluctuations of space-time itself when the universe is being created. Okay, and this is the plot that's going to be soon published. This is the review that Douglas and I were doing just before I started this trip. And you can see we had to lower the predictions of these guys by a factor of 10. That means we had to lower this scale by a factor of 10. We're trying to see these BB modes from tensors, but we're being buried in the B modes, the BB modes that are due to lensing, right? But we're still doing it, right? We're still trying to go forward and trying to do it. But we were able also to make a map of the lensing mass of the light coming from the early universe. If we think we understand the early universe, we can look and see what we see now and unfold it backwards and say, what's the lensing look like? There's the dark matter, there's whatever, it's all beautiful scalar, it has all the right kind of properties, and it's close to what your simulations tell you it should look like. So, all right, now I'm running behind because of the double pointers. So again, let me point to you, there's a beautiful picture of the microwave background so you'll be a little inspired. Here are the sets of experiments that are going on, starting from WMAP because Kobe's too far off the right. This is time in years. This is the effective sensitivity. It's a Moore's law and improved sensitivity of experiments Just like there's a Moore's law that improves computing power, and there's Moore's law for sensitivity of various detectors, there's Moore's laws for several things. If something is really important, people work hard, they do it. And there's a series of experiments coming along, and each one of them is falling on this line on average. It's because it's discrete. The experiments are done and you try and improve. We're falling on this law. Look at how much work has gone in, right? Why are people doing it? Well, because it's exciting, because you can learn stuff, and because the funding agencies are willing to let you do it. Right? It's comes down to that. But it's because we're really understanding the universe in a deep way. Okay, so here's the CMB S4. The site's going to be at the South Pole and up in the Anaconda Desert. And go a little quicker. You know, here's the kind of thing. And why do we do that? Well, let me show you this map of the world. Okay. Water in the atmosphere makes clouds and other things. Sometimes the clouds are visible, sometimes they're not, but they provide signal that screw up your data because you're trying to look at the stuff and you're counting photons. And you got, if you want to get to a part down to a millionth of a Kelvin or whatever it is, you've got to count 1 million squared photons, right? That means you've got to observe until that many comes in. So South Pole's a great place. The Andes is a great place. Tibetan Plateau and Greenland, except Greenland is having climate changes problems right now. And so another site, but China and the rest of the world aren't playing well together, is on the LACPT site on the Tibetan Plateau. It's one of the only one of two places in the north that is probably feasible to do it. And so here's what that site looks like. They're building telescopes there. They're building a place for CMB measurements. Here's a plot of a picture of the crew. This was shortly before COVID. I don't know how much it's slowed down because of that, because I was going to go, but I didn't. But it's a high altitude. It's over 4,000 meters, so you don't just go there by accident. And why do you go there? Well, our galaxy has got a lot of dust in it, so you got to look between the dust. This is the polarized dust. This is the straight intensity of dust. So you want to look in those windows. That's what's going on. Or if you're rich Japanese and have friends around the world, you can get JAXA to build you a satellite and launch it into orbit. And this is called Lightbird, which is designed to do the low L. So I showed you where it was going to go. Lightbird is scheduled. It's been slipping back some, but it's still moved forward. COVID slowed some things down, budget slowed things down, but it's going forward. So this is going to happen. There's going to be a fourth satellite for the CMB, plus these cities on the Earth, probably 2 or 3 cities on the Earth dedicated to worshiping the CMB, according to future archaeologists. In the meantime, our good friends finally discovered gravity waves, new kids on the block, and these gravity waves really are telling us some additional information about the universe, but it's not a surprise. And 2 of my colleagues and I are arguing with them, saying some of the things you're seeing are gravitational lens, and they say no, it's only 1 in 10,000 things should be lens. And I said that's true, but if there are 10,000 things, but you only see the 10 brightest, what fractions of them are lens? And I claim, up to half are lens. And so we're going back and forth. But LIGO is now gone through a period of being down and upgrading. It's back on the air. They're making 3 discoveries a week, according to what I hear through the grapevine. So they were making measurements slowly early. They got more sensitivity. They started making them faster. Presumably they're making them faster now. I wanted, even though I'm close to running out of time, I wanted to say a couple of things about the James Webb Space Telescope, because it's active, ongoing research, but they did something that was a little bit of a surprise to me. JWST releases their data to the world immediately. Now, there's a lot of people who are eager for the data, and not all of them know how to do science carefully. And so a whole lot of papers have come out, and some of them are good and some of them are not good. This is an experiment. We'll have to see how well it does and what its reputation is in the end. We'll see. So this is a big telescope. This part, there's radiation shields where the sun's on the other side and they're letting radiation go out to the side, trying to keep the telescope cold. this is about a human height. A human goes from about here to here, right? A woman probably goes from here to here. But it's a big telescope. It was all folded up and went up into space, and it unfolded. It's amazing how much it worked. It's amazing how much it cost. It's approaching $10 million. It's hidden. Nobody wants to tell you that, but it's really big bucks, and we'll see. But it's an improvement, and here's what I was telling you about what's going on. There's a Hubble picture. There's nearly the same galaxies with the JWST, and arrows pointing conveniently to galaxies you can see now. If you look carefully, you see a lot more detail in here. That's because you're focusing on the infrared here, and it's a bigger telescope. So the resolution's about the same, but you can pick out different knots and so forth. So this is really exciting stuff going on. A lot of stuff is coming out. Some of the stuff is not right. Some of the stuff is right. It's got to have to sort itself out. We'll see. But my team and I sort of was upset that they released the data so much because I wanted my graduate student and postdoc to have time to do a good job right and not be overswamped by what's going on. So we're using gravitational lensing. We're using the fact that a cluster of galaxy will bend light from a faraway galaxy and focus it, and it will make it brighter because it collects more rays and focuses it on it. So you can use it as an amplifier on your telescope. So what we're trying to do is view the very early galaxy by using gravitational lensing. So we had a part of a program where time is dedicated to looking at certain rich clusters of galaxies, to look at the galaxies in the background, and then trying to figure out the lenses, because we want to look and see what can we learn about the first set of galaxies and how they're doing. That tells us something about how quickly things started, but also nature of the dark matter, but also the dark matter is the primary component of clusters of galaxies. And if it was one of our favorite forms, that ultralight particles that are in a Bose condensate make up most of the dark matter in a galaxy, it'll be wiggly. It won't, cold dark matter actually is less granular. It's more fine-tuned than it will be when you have something whose Compton wavelength is comparable to the size of the center of the galaxy. So that's a really interesting project. So here's some early known galaxies from JWST. And nothing very distinguishing about these, except when you look at them carefully, they have a little bit of structure already. These are brand new galaxies. I mean, these guys are at redshift 8, right? The universe is 9 times smaller than it is now. Galaxies already exist, and they already have some structure, and they already have some of the elements. That first generation of stars went really fast. Well, they were supposed to go fast. Astronomers foolishly call them population 3, even though they're first stars. They are big stars. They burn fast. They blow up fast. And they put the material out there. But how can they have done that already? Oh my God, Does this mean we have to change things? Or does this mean we have some clue about what the deeper nature of dark matter is? I don't know. I thought I'd throw this in because I always found EWA students were really interested in whether we could tell about life on another planet. Here is one of the interesting spectra of one of the interesting planets that's been measured. And look, it's got carbon dioxide, it's got water, it's got ozone, it's got all these things in it, and including one of the ones that was just published, but I don't have a plot for it. It has elements that are usually only made by life. And people were going crazy about that. A little too early to tell, but the fact is we might learn something. Who knows? All right. I'm running completely out of time. So it's time for me to end now. Are you waving yet? Okay. All right. So we got this picture. We got the stuff. I made this picture with a data group, and I'll be able to, that's the thing that we're writing the paper for is the data group, which was charged with taking all the data from all experiments that are coming in and try and make some sense out of them and make some quality out of them. Now, originally for particle physics, but now I got us to do it for cosmology too. And so we'll see it. We got a picture for what goes on. We're living in this time, but I mean, there was a particle era, there was a pre-particle era, there was all kind of stuff that went on. And we got evidence about a lot of this stuff now. It's amazing, right? I don't know how much money we're going to make on this, but it's pretty amazing. I think I'll stop at this point. we can answer questions. Maybe my computer won't crash.
Okay, this is your session to ask questions. And if you just hold up your hand, microphones will come to you. Don't be shy. This is your chance to talk to George. While you're getting over any shyness, I will just ask George. George, you did mention at one point that sometimes research feels plateau and it's difficult to make progress. So one question that young scientists often ask when they're trying to choose research projects to work in, or fields to work in, or places to go, is how do I pick a place where it's likely that I might make progress fast? So is there a secret to picking the right research area?
All right, so you reminded me of a comment one of the postdocs here at IWA made. You know, we were giving a talk and I was saying, well, think about what research projects should we do, what should we be doing next right now? And the postdoc said to me, he says, you guys did all the easy stuff. And I've said, it's only easy now. It was hard then. Looking back, it looks easy. Once you know the answer, and once technology moves on, it gets much easier. You know, it's like a smartphone. You had to make a smartphone 50 years ago. It would have been really hard. If you have to make a smartphone now, you just go to the Apple store or the Hawaii store or whatever it is and buy one. And so the answer is it depends on your skill and your knowledge and your motivation. You've got to have those, because any good research project is likely, unfortunately, to have some difficult times, and you've got to be able to get over that hard part. But, you know, one of the things you look at and you see what people got Nobel Prizes for, and sometimes it was luck, sometimes it was skill, sometimes, you know, there was a chemist who used to brag, I worked on chemical compounds that smelled bad or were dangerous and might blow up because nobody else worked on them. That's how he had fields that were open and discovered. So when I started in cosmology, very few people were working in cosmology, but I knew it was going to be important before that. But there are things I think about now. What kind of research should I do? What should go on? And the answer is there are still very many opportunities. There are many things, many projects that are going to be important and are going to go straightforwardly in terms of what's going on. And things that I didn't know were going to be important when I was young turned out to be important later because we started moving in the quantum era. That is, quantum mechanics was always there, but we were still doing stuff in a classic way. You know, when we were building these early detectors, we cooled them. It was to get rid of the Johnson noise. Now I build detectors. I had grad students and postdocs now working on detectors that are cool so much that stuff goes down into quantum states. And you're using the quantum edges or the quantum devices, or in one case, the fact that you get, you know, Cooper pairs or superconducting pairs, and you can disassociate them with less energy than, you know, whatever. So I'm going to ask you a question. How likely, there was a famous set of double papers came out of Korea recently on a room temperature superconductor. How likely would it have been for that to be right if you didn't know anything about it? Well, you know it's hard. They can't be separate electrons. They have to be in pairs. What's the binding of electron pairs, right? How can it protect itself against, you know, 200 or 300 Kelvin or something like that, you know, 4/4 electron volt? Well, you got to find something that it is going to have a better binding than a 40th electron volt. Well, you can think about pressure or you can think about other things, but just to find it, it's going to be a tricky material. It's not saying there isn't one, but you're going to have to think very clearly about it. But it would be great, and it would help in many ways if you could find a room temperature superconductor. Should you approach that? So I always try and tell my graduate students and early postdocs, pick a project you think you can get done in 3 years. Then you'll get it done in 5, because it always takes longer than you think. But if you take something that's a really difficult problem, like I want to have a quantum internet connection, you know, everywhere, that might take more than 5 years, right? I mean, some things are going to be long and hard. So you have to think about it. You might say, oh, well, I really want to do that. I'll break it into steps. What really big advance can I make part way there that allows me to go in that direction. So it's a question of learning your judgment. I used to run sort of a game with my students, postdocs, where when a new discovery came out, was announced, what were the chances it was right, and how much of their time should they invest in going and learning more about it and trying to think it? Because if you're going to build apparatus to do it, and nowadays apparatus is in more than one form. We used to, for the experimentals, you had to build a detector or set up a laboratory experiment and do this kind of stuff. That's a big investment. It takes a certain number of time. For a theorist, some things you could write a paper in a month, right? So the investment and so on. But now for theorists, you often have to build a software suite or an AI suite or something that allows you to evaluate and do it. There's machinery that you set up. How much time and effort should I invest in trying to make progress in that? But what I used to do when I was trying to think about the next experiment, and this, my mentor, who was a Nobel laureate too at Berkeley, I had some that weren't, some that weren't, and he said, always stop when you come to the end of an experiment and think, should I just build a better apparatus to do what I was doing before? Because that's what I've been thinking about all the time. Or is there some new improvement in knowledge and in equipment and so forth that allow me to do science that hadn't been done before? And he did that, and that's when he was telling me and encouraging me, and that's when I moved into the CMB field. And because of that, I was doing other things, but it was cosmology, indirectly cosmology, but I realized we've gotten to the point where we can start building apparatus to do the CMB. Now, that was easy then, right? Not so easy because we didn't have good sensitive detectors. We didn't have the right kind of antennas. We didn't have those kinds of things. And it's getting harder now. It's a huge number of people. I mean, you saw those cities, there's thousands of people working on these kind of things now because it's so rich. So you're better off doing something you can do at your own pace, and you can learn and do that kind of stuff. But sometimes something is so important and so fast, you want to jump in and get it with a big team. So the advice I give is to think carefully, see what your skills are, and then, see if you think you can get something and get done in a reasonable time.
Thank you. Anyone feeling courageous? Great.
Wait a minute. I want to come here for a second.
Who?
Yes, please. Just for a second, just walk up.
Who? Which one? The person asking
the
the
lady
question?
that asked the first question. She was brave.
Who was
She
brave?
did first.
Which of you was brave?
She didn't say her name.
Who raised their hand first?
She did.
I thought it was this one.
You get this if you come up. You get this. I give you the prize. Yes. You can have the prize. See? Being brave is a good thing. She got the Nobel Prize. It's chocolate inside, but I don't know. I would keep it.
So, who has the microphone, though?
She does.
Good.
Okay. First, I should thank you and everyone in this room for this great opportunity to learn. And I participated on the Nobel Prize dialogue the day before. And so the last question there was they asked about your best teacher. So I'd like to ask for your best students. So are there any characteristics or attitude you think that would help a student in studies?
Oh my goodness. I thought you were going to ask me who my best student was, and I was thinking, how am I going to pick? Because I have had several that were very good. I have one that just got his PhD that I think is truly outstanding because he's a whiz in the lab and he's smart academically, and he goes and do stuff on it. But the fact is, it's the people that have the can-do attitude. They're saying, I'm excited about this research. I know I can do it. I will learn. We were making position-sensitive basically avalanche diodes for single photon counting. We had to convince a manufacturer during COVID to manufacture these gangs of avalanche diodes together with a readout so we could interpolate which one was doing it. He managed to go and convince the manufacturer to make a run on that, even though the factory was partly closed. What does that tell you, right? There's a lot of stuff going on. He's working in the lab. He's learning the science. He's doing what it takes to move the experiment to the next level, even in adversity. Right? And so it's the willingness to buckle down and do the job. It's the thing. Unfortunately, it takes a lot of time and energy.
Thank you for your answer.
Let me follow up on that. When you were these guys' ages, how much time did it take? How hard did you work as a student?
I don't remember when I wasn't working. I mean, I was at MIT, and there were a lot of smart people around. And I didn't want to have to be the best, but I didn't want to be stupid. You know, I wanted to do, and then I got a thesis advisor who said, here, we're supporting you, build your apparatus. And this was a great, huge apparatus that we used at Brookhaven Lab for particle physics. We built this really monster. He trusted us with a bunch of stuff. I repaid him one time because he would be teaching, and he flew down to Brookhaven, and he comes in the middle. You know, I'm running, Orrin Fackler and I are running the night shift, and he comes in all full of energy and excitement. And we had got osmium as a target because I calculated that we need the densest material we could in order to make a K plus beam turn into a K0 beam so we could do a test. And I had to take a file and so forth because it didn't quite fit because things were, and there was all these pieces of shiny silver there on the counter, and he comes bonding in, and I go, it's really hard work shaving this osmium platinum down to make it fit in the target box. And he looked at me and he said, this is why I got my grade. Looked at me, he's having a heart attack, and he goes, I said, what's the matter? Is it toxic? And he looks over at Orrin, and Orrin, who was really a straight arrow and everything, didn't say anything, which is good. And he said, no, but it's precious. And it's all signed under his name. He has to deliver it all back.
Yeah. More questions? Do you have one? Okay. Oh, sorry. Go there, and then we'll go to the back. Yes, please, and then you.
Hello, my name is Sewan Park. Thank you so much for the interesting lecture. My name is Sewan Park, and I'm majoring in science education, especially in physics. So these days, there are so many researches on education, such as socio-scientific issues, or as you have mentioned, STEM. So my question is there a specific kind of education that you think that helped you to continue the research and in the end actually get the Nobel Prize?
Oh, this is hard. I can't remember back that far. You know, when I was young, I was struggling and working very hard and trying to learn everything. And I had the advantage that I had parents who helped. You know, my father taught me calculus, so that by the time I got to college, I wasn't struggling through that because you need a lot of math to do science. You need a lot of other stuff. But I've been thinking in terms, it's been so long, I've been thinking in terms of education myself. And what I learned is the best way to learn is to do it yourself, right? And so when I was here at EWA 1 year, you can figure it out. I have to go look it up. I was teaching a class, but I also had gone over the Seoul High School for Science. And I think that people learn best by hands-on. So I gave them an experiment as part of their homework was to watch the transit of Venus across the sun. Taught them about how to make a pinhole camera, and then you make the projection on the ground, and then you can watch and time how long it takes, and made a connection to a school in Australia to try and do it. And I have to say, the Seoul High School science guys put a lot more enthusiasm into it than my EWA students, but both of them got excited about it, and some people did a really good job. And they really learned a lot, and they measured how far it is from the sun to the earth. And the high school students worried how come their answer wasn't exactly the 150 million kilometers. And they didn't, so they even gave a talk and presentation about why they, what kind of errors there was. They didn't understand statistics. So it used to be when I started my class, I would try and very carefully teach the students in science. We believe there's an external reality, and that all competent observers observing that events in that external reality will report the same basic space-time events in the end, right? Photon left here, a photon came here, there. That kind of existence of reality. The other one that I think I would teach them is that humans are easily fooled. And I'd first give them some optical illusion kind of things. And you get prejudices, and there's one I have looks like a snow on a rocky hillside. And then if you look at it for a minute, you think, oh, there's two horses standing there. You cannot unsee the horses after you've seen the horses once. You have prejudices and so forth. But truly, you don't have statistics. And so one of the questions that I gave them sort of as a homework question, you get a breast exam and you got a positive return for breast cancer. What are the chances that you have breast cancer, right? And the answer is a very small number of people who are young have breast cancer, and the tests have a good outcome, 85% or more, that they get a positive result. But there's a huge number of people that don't have breast cancer, and the failure rate, the false positive rate is very small, but there's so many people, it's about 4-to-1 chance that you didn't have it. You should have the test again before you get panicked. Of course, you're going to get nervous anyway. So learning about statistics and fluctuation, really hard for humans. They have biases, they have all kinds of stuff. And so there is a whole way of having to learn to think about stuff and do that kind of stuff. So when you're teaching science, you have to put a bedrock, you have to say, here's the assumptions you're making, and then this is how you learn and do science.
Thank you very much indeed. Thank you. Could we have a question? There was a question back here. This lady here. Oh. Okay. Yes. Go on then. That's fine. Yes. Please. But then you.
Okay.
Okay, hi. My name is Heejun, and I'm a master's student who is majored in electrical engineering. And I'm a beginner who started research recently. So this is the time that I'm failing every experiment that I'm doing right now. So I want to ask you how you endure the time of failure and believe in yourself that it will make work.
You get that? When things, how do you get past the thing when everything's failing? How do you motivate yourself when everything's going wrong in research?
There's two sets of answers that are relevant here. The first is there's never been in my experience any graduate student who just came to graduate school and sailed through the exams and sailed through the courses and then sailed through doing the research. Every single one of them has had some crisis point where they'd come in, the lab equipment didn't work, or their computer kept, dropping out, or something happened, and they had to find it within themselves to figure out how to get around that problem, either by doing it over and over again. So there was a real recent example of that happened in this kind of stuff. So there was a breakthrough experiment in fusion about 7-8 months ago, and that was the first time that at the Fusion Innovation Center, which is in California, they put in 2 megawatts and got out 3. That means they actually did fusion reaction, right? The thing we'd like to have for the future to be able to provide a lot of energy. And then they could not make it work again for almost 4 months. Somebody had improved it. And, better is the enemy of good enough, right? As we say, if something passed the test and everything, don't mess with it unless you really have a big improvement. And it's sort of surprising. There's millions of dollars and everything at stake, and people really want to see it. They finally, somebody, this is inertial confinement fusion. So you have this really high power set of lasers, and you put them all together, and then you make like 19 separate beams that are coming together and going to collapse a little droplet of fusible material and do that. Well, everything's got to line up exactly right, time-wise and everything else. And somebody ticked something right, and it didn't quite work. And they redid it, and they celebrated the fact that they redid it. So the fact is, even big professional teams with millions of dollars behind them have these struggles, right? And so it's something you have to be able to overcome. But that's what fairy tales and a lot of these folk tales tell you about. It's the hero's journey. The hero overcomes. The hero comes, face problems, he overcomes them, and ends in success. Yeah, it's true in life. You're gonna have trouble. If it was really easy, it wouldn't be new research. Unless you really picked well.
Thank you. Okay, do you want to pass the microphone to this lady? She's been waiting. Thanks. We're running out of time here, so maybe this is the last question.
Well, that's because I talk a lot.
Okay, you ask.
Hi, my name is Minji Ko, and I'm a junior student in earth science education. And it's a huge honor to have a chance to be in your special lecture. Seriously, it was the best moment I have had in Iwa. And my question is, did you have any specific particular motivation or event that you decided to be a part of a cosmology among that enormous scientific field? And do you have a ultimate goal that you pursue or dream for good?
Yeah, I am thinking about it. One thing that I remember a lot is that I wanted to know how things work. When you're a young child, there used to be a joke about if you're a young child that's going to be a scientist, when you get a present or a watch, you take it apart and see how it works. If you're going to be an engineer, you take it apart and you put it back together and it works, right? Or it may even be better. I always wanted to know how things worked. I really like the idea there's an underlying order and plan to the world, and that you could understand that and that you would know stuff. And it was a great pleasure for the few times I made discoveries to say, I know this and nobody else does yet. It's like I got here before, it's like you're in a video game and you got there first. But in the end, you're doing it because you're going to turn around and publish and tell everybody. Right? And it's funny because you wouldn't think that'd be a primary motivation, but I found that I really wanted to know how things work and understand why things are the way they are.
I think if I can comment just very quickly, students around the world ask exactly that question all the time of Nobel laureates. They ask, what is your motivation? What keeps you going? How do you overcome failure? All the rest of it. And the answer is always the same from Nobel laureates. It's almost like they don't understand the question, because they say, what I'm trying to find out interests me so much. What else was there to do? I just want to know the answer to this question. It is what motivates me. It's what keeps me going. It's everything. I just need to know. And I think that's, in a way, the great luck that you Nobel laureates have.
Yeah, and they paid me to do it.
Yeah, exactly. The question begs to be answered. You just have to know. And it's that deep curiosity which we see again and again. And I suppose the question is, if you don't feel it, if you're not burning to answer a question, can you make it? Can you develop that?
Well, I mean, if there were psychiatrists here, they would say I'm an INTJ. There's about 1 or 2% of the population that really have to know stuff like this. There's other people who want to be ice skaters or ballet dancers or whatever because they like the physical activity. That's a bigger percentage than there are scientists. but,
Yeah, but you've got-
there is some instincts, right?
But you've got scientists here, so how do they make themselves into you, I suppose, is what they want to know.
Well, they don't have to be me. They have to be themselves. They have to figure out what are their talents, what interesting problems do they see. Are there some problems that if they help solve, it will help mankind a lot, a big change that's going on. We're facing a time now, which I think is going to be unprecedented in terms of global challenges. And as I told Anna, I don't think there'll be a time for the next 20 years when we don't have at least 2 crises going on. And we're going to need people to solve those problems.
Thank you.
Thank you very much.